The Sun. This star has always fascinated human beings because of its lightning beauty and most of all because of its infinite amount of energy. This energy comes from nuclear fusion, a nuclear reaction in which several atomic nuclei encounter themselves and give at the end a one-piece atom. Man, whose inventions are always inspired from the nature, wants then to recreate this endless and useful source of energy. But how will they be able to build a tiny sun? Let's go back to the 80s. It's at the Geneva Summit of 1985 that the idea of an international project first appeared. It was proposed by Gorbachev as the Russians were working on tokamak reactors. Tokamaks are reactors in shape of torus using magnetism to study plasma and nuclear fusion. In 1986, the United States of America, Europe and Japan decided to join the Soviet Union in its project. And then the idea of building ITER was born. Different periods followed, and at the same time, other countries decided to join the group. From 1988 to 2002, we assisted to 3 periods. The first one, the conceptual design activities, gathered every other studies, which were made about other similar past programs. The engineering design activities decided to propose the cost of ITER. The coordinated technical activities prepared the construction of ITER and where it would be. After long debate, it was chosen that Cadarache in France would be the site of ITER. In 2006 was signed the final agreement and the construction started in 2007. The ITER mission is to demonstrate the feasibility of nuclear fusion as new source of energy without negative impact. The project wants to be used as thermal source of energy to create electricity. It will create more energy in less time than any other devices used nowadays, as 20% more than a basic thermonuclear reactor. ITER works with the nuclear fusion principle, the one happening on the Sun, with deuterium and tritium. Deuterium, or heavy hydrogen, is one of the 2 stable isotopes of hydrogen, and tritium is a radioactive isotope of the same atom. When both fuse, 2 nuclei come together to form a helium nucleus, also called alpha particle, and high-energy neutron. These isotopes are very interesting for our reactor because their fusion requires less energy, which means less temperatures. Activation energies for fusion are most of the time high because protons repel themselves as they have the same positive charge. For fusion, nucleus must be able to get within 100 femtometers from each other, so they can undergo quantum tunneling and pass through the strong nuclear and electrostatic force. In ITER, this distance is made possible because of its high temperature and its magnetic confinement. High temperature give the nuclei enough energy to overcome their electrostatic repulsion. For deuterium and tritium, the optimal reaction rates occurs at temperatures on the order of 100 million Kelvin. The plasma is heated to a high temperature by ohmic heating. With these high temperatures, the plasma won't be stable, so it needs to be confined. A working reactor needs to contain the particles in a small volume for a long time, so most of the plasma can fuse. This is where the magnetic field appeared. A charged particle moving through a magnetic field is exposed to a force perpendicular to the direction of travel, resulting in a centripetal acceleration thereby confining it to move in a cycle. A solid confinement vessel is also needed to protect the equipment from high temperature and energetic particles and to maintain a near vacuum for the plasma to populate. The containment vessel is subjected to a barrage of very energetic particles which can degrade the structure. Once fusion has begun, high energy neutrons will radiate from the reactive regions of the plasma, crossing magnetic field lines easily because of its neutral charge. Neutrons receive the majority of the energy, but alpha particles will also expand their energy in the plasma heating. This heat energy will then be used to power an electricity generating turbine in a real power plant. ITER is made of different components. First, we have the vacuum vessel, which is the central part of the ITER machine, made of steel and in which the plasma is contained by magnetic fields. The breather blanket is used to produce tritium with the reaction of lithium isotope and high-energy neutron from the plasma. The central solenoid coil will produce a field of 13.5 Tesla. The cryostat is a large steel structure surrounding the vacuum vessel and the superconducting magnet and is used to provide the coolest vacuum environment. The ITER will use an external water cooling system which will evacuate most of the energy by loops out of the machine. What's left will be used for tritium production. Nowadays, the project is in construction in Cadarache. It will end in 2020, later than it was expected to be, and will cost 20 billion euros, twice more than it should have been. The ITER project is also criticized. The first critic comes from the potential danger of this reactor. Indeed, it is not absurd to consider that with the use of tritium, a radioactive element, this machine could turn into a devastating bomb. Above all, when we know that Cadarache is situated on the most active fault in France. The second critic is about the very feasibility of this project. The physicist Sébastien Balibar said, "We say that we will put the sun into a box. The idea is pretty. The problem is we don't know how to make the box." He is talking about the lack of experience in fusion reaction, of the control of tritium massive production, and the knowledge about building a 100% safe vessel. About the future of ITER. The operating phase should start in 2020 and last 21 years. The actual period of use is expected to be 400 hours. As soon as the operation phase is done, the installation will be deactivated during 5 years and dismantling during 10 years, in due to the laws about radioactive waste. After ITER, there will be another experimental program called DEMO for a demonstration power plant. The first industrial reactors are expected in 2050.